Hello everyone. In this video, I'm going to be giving you an introduction to proofs in propositional logic. So this is going to be, doing proofs is what we're going to be doing for most of the rest of the semester. And a huge part of our grade is going to be based on how well we do these. And it is quite challenging, but I think that by learning a few simple skills early on, if we devote ourselves to thinking about this, reading about it, and practicing it, and seeking aid from me when that's not enough, I think we'll be able to, I think a lot of us, almost all of us, will be able to be successful in this. And please let me know if you are having difficulty. It's not unusual to have a lot of frustration when it comes to this, but frustration is something that can be overcome. So just before we begin, I'm just going to tell you a little bit about the broader scheme we have here. We've been working on chapters 10 and 11, and this whole section of the book from chapter 10 all the way to chapter 21 or 22 is one big part of the book. And we're not going to touch on every chapter. We're going to select the essential chapters, and then I might give you some guides. Some of you might find some of these skipped chapters to be helpful, but my feeling is that for the most part, they are distractions, that they prevent us from getting to the real meat of the subject. And so I'm actually going to be bouncing around a little bit and not necessarily presenting all of this stuff in the same order or in the same way, at least initially, as the book does. So that means that in this video, I'm actually making this as part of a 3-video group. This is going to be the first one of 3. And in this video, we're going to jump all the way forward to chapter 18 to look at some of the basic elements of constructing a proof. But along with this, I'm going to have a video on an introduction to truth tables, which is discussed in chapter 14, and a introduction to truth functional language, which is introduced in chapter 12. And my idea here is that instead of giving you the full version of any of these in the same order as it's done in the book, they start with truth functional language, then they move on to truth tables, they spend 4 chapters on truth tables, and then they move on to the proofs themselves. What I'm going to do is I'm going to kind of like give you a beginning of these 3 different parts and then bring these things together. So my kind of conception of how we're going to do this is that this video is on proofs. We're going to get an introduction to proofs. We're going to get an introduction to the truth functional language, which the book abbreviates as TL. We're going to stay with TL to keep things simple. And then truth tables, which I'll abbreviate as TT. We're going to bring these up individually, just getting a basic introduction to each, and then we're going to bring these together until we have this more fully realized version of proofs in the coming couple of weeks. So it's going to be important that you listen to all these videos, watch them, do the practice problems, and then do the quiz while referring back to these, okay? So with that, let's get started here. And I did do some of this in one of my classes on Monday, but I didn't quite get to it in my other class. So we're going to just kind of start afresh, which might be useful for all of us anyhow. So the idea with a proof is similar to a categorical syllogism. We're going to see a number of lines, 1, 2, and so on. And these represent different premises. Okay, so this would be like premise 1, this would be like premise 2, and so on. Now, in categorical syllogisms, each argument had 2 premises and 1 conclusion. That's not necessarily going to be the same as it is in propositional logic. Propositional logic will actually allow us to do arguments that are many, many premises long. The shortest ones will be as little as 1 premise. And the longest ones, we won't deal with it in this class. Probably the longest we'll deal with in this class are 8 or 9. But there's no real limit to how large a proof can be. And it might be helpful to think that computer code is essentially a version of a proof. And that can be, you know, millions of lines long. I'm not a computer programmer. I think that simple programs can be just a few lines long. More complicated programs, most of the programs that we use are probably a few thousand lines long, using languages that are themselves computer programs. And every once in a while I see like an old software program that is still being actively updated celebrate milestones like hitting their millionth or their billionth computer code. Obviously the work not just of one individual, but of often hundreds of people. But I promised myself not to go on any tangents today. We'll stick to the point. So let's move on. So the way we're going to represent this in logic is that on each line, we're going to have a different premise. And we're going to learn these symbols under the truth functional language. But for today, I'm usually going to give these lines as simple. The only thing we're going to abbreviate is the statements themselves. So you might recall in earlier videos that a single letter like this, A, in propositional logic, it stands for a full statement. That is different than what letters stood for in categorical logic. In categorical logic, the first thing we did this semester, we have something like all SRP. These letters stood just for terms like cats or animals. Now our letters are going to stand for full statements. So what is a statement? Again, just as a review, a statement is any sentence that asserts something is true. So in fact, all SRP is itself a statement. And what we can learn, one of the interesting things about this propositional logic is that it will put the whole statement gets compacted into just a single letter. And what that sentence says doesn't actually matter anymore. We have abstracted past the sentence, past the meaning of the sentence, to the point where all sentences carry the same meaning. And the meaning is simply that it carries a truth value. And it still functions in an interesting way. So like all the philosophical issues of that is a discussion for another day, but that means all SRP can be abbreviated as I. That means that Springfield is the capital of Illinois, can be abbreviated as an A. That means that Chicago is the capital of Illinois, even though it's false, can still be abbreviated as an A. The sun is the largest celestial body in the solar system, that today is election day. All of these are statements that are either true or false. Sometimes unknown, but still either one of those two. And they can all be abbreviated with a single statement, okay? Now, in addition to that, we will understand that when we look at a premise, we're going to understand that the entire line, the line as a whole, is going to be taken for the sake of the argument as true. So when it says 1, this is indicating premise 1, A, it's suggesting that A is true. Now, what's important is like that doesn't always mean that every letter on the premise is true. So here when we have A by itself, this is what we might call a simple statement. In other words, this is as small as it can get. It can't be broken down any further. We're given one statement with no additional operators. Compare that, on the other hand, to a statement like B or C. Now, this is a premise. Now, in B or C, let's put this over to the side, B or C. As a premise, we understand that the whole thing is taken as true. And we might recall, I'll just keep reviewing some of these older things, but in this case, the word or means at least one of these is true, possibly both. Remember, this is the inclusive or, the broccoli and carrots version of the or, that at least one of these is true, possibly both. Even if this whole statement is true, and it will be taken as true, that doesn't tell us if B or C taken as individuals are true. So if you saw this on a line, B or C, and I asked you, is B true? And you would have to say, I don't know. We don't have enough information at this point. And I would say, I might ask you, well, what is C true? And at this point, you still would say, I don't know. I don't have enough information. But I can tell you that at least one of them must be true. And you know, again, that one of them must be true because the statement as a whole is taken as true. The A, on the other hand, that's the simple statement. There's no other possibility. And that's one which you kind of have to wonder. If the statement as a whole is true, what are the possible truth values of the individual statements? And so here, since we have only the one statement, and I asked you, what are all the possible truth values? The only way to break it down is to say that A is true. So for the sake of the argument, A is true. On the other hand, if I were to ask, what if premise 2 is true, what are the possible truth values for B or C? You would say, well, B is still either true or false. I can't tell. C is either true or false. I can't tell. But I do know that at least one of them is true, right? On the other hand, so let's look at our last operators, and just to remind you, what are our operators? And this would be a good time to review this. Remember in math, we have a few different operators: plus, minus, multiplied, divided by, so on. We have operators in logic too. These are and, or, if, then, and not. Okay, those are our 4 primary operators. There is one more, but we're going to talk about this on a different day. It's called logical equivalence. Logically equivalent. So we can say it's logical equivalent. We can say it's logical equivalence, whatever. Okay, so each of these has its own meaning. Now, we recognize that in arithmetic, we have symbols for these to help us convey our mathematical functions more simply. For plus, we have the symbol of like this little cross. For minus, we have a symbol of a little dash. For multiplication, we have a symbol of a little X, and so forth. In logic, we also have symbols. I'm not going to use them today, but let me just introduce them to you anyway. I'm going to show you 2 different sets. First of all, there's the typical set. So most logic books will use one set of symbols. Our book uses a different set of symbols. And then, and I don't know why actually it uses a different set, but I'll show you what those are just so you understand, and it goes through this in the book. And then I'm also going to give you a few alternatives for our class. Because you're going to be typing these in, I want to give you symbols that you can just type. And you'll find that some of these symbols you have to reprogram your keyboard, which we're not going to get into in this class. So if you use those, if you figured it out for yourself and you use them, that's fine. I'll understand what they mean. So typically, historically, the and is just this little dot. And it could be something like P and Q. It would be read as P and Q. The or is read as a little V. Like this, P or Q. The if then is read, looks like a sideways horseshoe. Sometimes we just call it a horseshoe. It would be something like, this is weird because you say it, like here you say P or Q, but here you say if, there's no symbol for that beginning word, but it's just a symbol. If P, then Q. And then not is this little tilde, and this just gets attached to one symbol like this, not P. For today in these proofs, I'm just going to be using and, or, if, then, or not. Our book basically uses these same symbols, except for the and. They use what's called the ampersand, which is just Shift-7, I think, on the keyboard. And so we're going to, because this is easier, the ampersand is easier to type in than the dot. We're going to use, because this is not a period, that would be very confusing, I think. We're just going to use the ampersand. And then for the horseshoe, so the book uses all the rest of these the same. But for the horseshoe, just do 2 dashes and a wedge. The dashes are just by pushing the key next to your 0 button. And then the wedge is, if you look at your M button on your keyboard, you look 2 over, you see the wedge pointing to the right. If you type that. And if you're typing this in most word processors, if you do dash, dash, wedge, that'll just come out as an arrow, which I think will be good for our purposes. Okay. So this is I'm just priming you for this. That's not the subject of this video. Let's get rid of this then. But our operators are and, or, if, then, and not. Just get rid of this. Okay. So going back to our basic proof, let's take a look at this. And actually what I'm going to do right now is I'm just going to remind us of our basic forms. I'm going to pause the recording so that I can just write all of this without wasting your time, and then we'll start it up again. Okay, what you see here on the right are our 4 basic forms. And we're going to be learning more forms moving forward, but these are the bedrock. And I want us to make sure we learn these really well before we start adding more into the mix. So on the top left, we have modus ponens. If A is true, then B is true. A is true, therefore B is true. Modus tollens. If A is true, then B is true. Not B is true, therefore not A is true. Disjunctive syllogism. A is true or B is true, but B is not true, therefore A is true. Or it can be in the reverse. If you said not A, then it would go to not B, B. And then finally, hypothetical syllogism. If A is true, then B is true. If B is true, then C is true. Therefore, if A is true, then C is true. Okay. Now, the idea with a basic proof goes something like this. Lost those instructions, that's okay. So I'm going to start you off like this. Given a set of premises, and get ready to pause your video. When I say pause next time, just go ahead and pause it. I'm going to ask you a question, and then I will say pause. Figure out the answer, and then press play again when you are ready to check your answer. Premise 1, let's say if A is true, then B, A. Now, if these 2 premises are true, what comes next? Now, this is kind of like an addition problem, where we say, all right, this is true, number 1 is true, and number 2 is true. What comes as a result? Now, the purpose of the forms, I suspect that many of you will be able to make a conclusion from this already. The purpose of the forms is a kind of handy key for us. That when we see these premises, when we see the pattern appear in our argument, we know that we can just take that form and apply it to an argument, regardless of what other features of that argument are. So if we look at this, if A, then B. Now we see line 1. We want to ask, where does line 1 fit? And we see actually 3 different arguments with if A, then B. We see modus ponens, modus tollens, and hypothetical syllogism, all with that first formulation, if A, then B. And by the way, if it said something like, if K, then S, oh, those are my initials, that just happens. That would be fine too. Like if A, then B, it doesn't really matter what the letter is, so long as the pattern, the form, is met. So at first, from premise 1 alone, all 3 of these are a candidate, but we can only pick a form where we have both of these lines fulfilled. And here we see A. In other words, we see how this letter matches this letter we need a form where this letter matches this letter. And here it does. Here it does not. Here it does not. So modus ponens is the only thing that's allowable. And then from there, we see the B come down. So the question, and I basically gave it to you, but the question is, which of these four forms replicates this? Or another way of putting it, what comes down here when you put these two premises together? What comes next? And which of the four forms did it use? Pause. Okay, by now you should have figured it out, and you probably said B. That is correct. If A is true, then B is true. That doesn't tell us by itself that A is true or that B is true. But we do know that A is true, given premise 2. That gives us, in the end, B as being true. So that we just did logic. We just did logic, the most fundamental move of logic that all other aspects of logic are based on. Now the question is, which form did we use? And the answer, of course, is modus ponens. Modus ponens, I keep saying that. We use modus ponens. So what we're going to do as part of our proof, we're going to want to label every step. For every step as part of our proof, we're going to want to say, which form did we use and which lines did that form apply to? And in this case, because we use modus ponens, we're going to put MP, the abbreviation for modus ponens over here, and we used line 1 and 2. That matched line 1 and 2 of the actual form. So we're going to write modus ponens 1, 2. That is essentially proving that B follows from our two premises. Okay, that's what our proof is going to involve. But this is the most basic version of it. So let's do another one. Let's do a couple more of this level of difficulty, and then we're going to step it up a little bit. For the next one, we're going to do this. If A, then B, starting it off the same, not A. I'm going to ask you to pause here. What comes next? If A, then B, that's premise 1. Premise 2 is not A. What comes next? And which form did it use? Pause the video and see if you can figure it out. Okay, by now you should have figured out what comes next. And your answer should be nothing. These don't fit. This is not the same form. This is not the same form. We're often going to run into things in our proofs where we're going to feel like, oh, this is so close to one of our forms. But if it's not precisely the same form as what's been established as one of our valid forms, then it's not going to work. Sometimes that might even be, it might even be the case that we write a valid conclusion. But we have to use the forms that we have established. And just as a little more background, it's because we have other proofs for these forms. So it's like the forms that we're being given are our pre-proven forms, which we can use in their variations. We can use as sort of tools to make our proofs for these new arguments. And then I'm going to show you later on when we get to truth tables, I will show you how to prove that these are valid. But for now, it's important to note that if A then B, not A, does not fit either modus ponens because there is a not, or modus tollens because this was denying the antecedent, meanwhile this denies the consequent. And as you might remember from our earlier sessions, this is not valid, that's a fallacy, whereas this is valid, that's right. Okay, let's step up the difficulty a little bit. Now, I'm going to break this down into a few different questions. Let's give this argument, let's say J for k. 2. We're going to say if k, then not. I'm sorry, I was about to make it more complicated than I should right now. We'll get to a more complicated one later. If k, then m. And then if, let's say, not j. All right. Now, this time, I'm going to do something a little different. I'm going to tell you, I'm going to give you a conclusion. And our conclusion is M. Now, my question for you, and this is going to take, I definitely think you should pause the video and see if you can work out an answer. It's going to take more than one step to get from the premises to the conclusion. In other words, you're going to have to apply the forms 2 times in this case. And you're going to, what you're basically going to do is you're going to use one form and 2 of these lines to create a 4th premise. In other words, what comes, if you were to take 2 of these lines and put them together, what could you conclude as a valid conclusion from these? What new premise could you create from those premises? Then once you have that, you'll write that here. This is your new line. And then make sure to put the form and the lines that you used. Then use this premise along with another one from up here, maybe the same one, maybe it's one you've already used, that's fine, to come up with a new premise. And what you are trying to do is get to this conclusion. And this could keep going for a long time. But you're going to try to ultimately want to get an M all by itself. This is the puzzle. So the easiest question to ask is, which 2 forms do you think is going to be required? And see if you can take those pieces that I've just given you and fill out lines 4 and line 5 to get M on a line by itself. All right, here's the pause. Pause the video. If you're listening to this, you should have figured it out. And so the answer for this, and by the way, as these problems get more complicated, there are going to be multiple correct answers. Some of them will require fewer steps than others. But for now, these problems are so simple that our first problem is going to be it will tend to have only one correct answer, maybe just a variation of the one correct answer. The forms that should be used here are disjunctive syllogism and modus ponens. Modus ponens. Okay, so what does this mean? Now let's take a look at which one should we use first. Would it be modus ponens? The answer is no. And the reason why is, if we looked at this, if k then m, that's what our first line is for modus ponens, right? But that requires an A, and it requires an A to be true. Here, it would require the K to be true. But there's nowhere in this argument that tells us K is true, not immediately. In order to use modus ponens on line 2, first, we have to establish that K is true. And for that, we want to use disjunctive syllogism. So look at this. Line 1 says, either J is true or K is true, possibly both, right? Based on line 1 alone, the only thing we know is that at least one of these is true. But we go down to line 3 and it says J is not true. If J is not true, but at least one of these is true, that forces K to be true. That's what disjunctive syllogism is saying. Either A is true or B is true, but B is not true, therefore A is true. So we're going to take these two, J or K, not J. And what's essentially happening is that we know, let's break this down. In a disjunctive syllogism, we know that J is either true or false, and K is either true or false, but one of them must be true. Line 3 says J is not true, so it must be false. And one of these must be true. That leaves K as the only possibility. So now we're going to be able to take K down. You don't have to draw this arrow in the actual proofs. This is just me illustrating it for you. We can put K on a line by itself. Then we're going to write DS for disjunctive syllogism, line 1 and 3. Okay. Now we have essentially established a fourth premise. In a way, it was a conclusion. It was a conclusion from premises 1 and 3 alone. But now that we have proven that this is true, when these two are true, we can now build from that K for a future conclusion. Now we look at line 2, it says, if K is true, then M must be true. Well, since we have now established the K is true, that allows M to be true here. From line 2 and line 4, MP, we have proven that M is true. Now look back here. Our conclusion said M. As soon as we get to something that is identical to the conclusion, not just having M on a line, but having M as the entire line, we now know that we can prove M is the valid conclusion from these first 3 lines. From 2, 4, modus ponens. And that's the proof, okay? So if you got that, congratulations. If you did not get that, please go back a few minutes, read through this again, see if you can work on it until you figured it out. Things are only going to progress in complexity from here. Well, with that, let's delete this. And let's do one more for this video. Let's make this one a little bit more complicated. We're going to start off if not B, then not C. Then we're going to say if not C, if not C, then D. F or not B. Not F. All right. And then for the final line, we're going to say that our conclusion, and by the way, you could probably come to a conclusion if once you've worked out all of these, what is the ultimate conclusion of all of these premises? But we're going to say that the answer is D. So now your quest is to figure out which forms are going to be required. And just like before, see what if you can figure out line 5 using 2 lines and 1 form. Then line 6. Let me see how many this would take without showing you the answers. That would take 1 step, 2 step, 3 steps. I think it'll take 3 steps to get to your conclusion. And I think for this one, there is going to be 2 variations for how you can get the answer. So go ahead and pause your video. And once you have the answer, go ahead and press play again. So go ahead and pause. Okay. If you're listening to this now, you should have come up with an answer. And we're going to go through 2 different ways of getting here. Okay. So first of all, one of the curveballs here is that we put the nots inside. Now, what's important here is that, like, when it says not be versus not be here, if I can get this by itself, so let's look at a statement. If it says if not be, then not C, not be, there's often a mistake that's made where some people will think that this is denying the antecedent and is therefore a fallacy because this line has the word not. And this, the form says, doesn't have that not. And we've already been told that if this said not A, that would be a fallacy. That would not work. But there's a big difference here. And that's that here our not A is the same as what our antecedent is. So even though there's a not, we are affirming this antecedent. And therefore, we get not C. Strangely, surprisingly, although this might make sense to some of you, and hopefully it'll make sense to everyone soon, if premise 2 said B, then we will not get C. There would be no valid conclusion there. If premise 2 was B, we would not get C. We would not get not C. That would be the fallacy in this case. What's important again is that we agree that there's an agreement and equivalence between what this premise is and what the antecedent is. All right. So I already asked you to pause the video. If you trip that up, you might as well go back and try to figure it out again. But if you're ready to move on, let's do it. So I'm going to give you 2 solutions. One solution is like this. We notice we have 2 conditionals in lines 1 and 2. Furthermore, this not C agrees with this not C. Sounds like I'm saying not C, and I'm really obviously did not intend for that to be the case. I'm sorry. I wish I could go back. Especially on election day, it seems pretty. I've never thought about that. I've been teaching this class for 11 years, and I probably said not C 1,000 times and never realized what it sounded like. If not B, then not C. If not C, then D. This has the same form as hypothetical syllogism, which allows us to take the first antecedent and the second consequent and put them all together in a single conditional. So we can do that here to get if not B, then D. Right? Now again, this is one of 2 possible solutions. So if you didn't start off like that, that's fine. You might have the second one, which we'll go over. So this was from hypothetical syllogism 1 and 2. Now, we can also look at 3 and 4, where here we are denying, line 4 says, it is not the case that F is true. So that denies this part, which affirms this part. So we're going to take this and bring it down here. This gives us not B, and that comes from disjunctive syllogism 3 and 4, right? Now we see this agrees with this, just like I was showing up here, except now we have the D. If not B is true, then D is true. Not B is true. In other words, B is false. If B is false, then D. So that gives us D down here. That comes from modus ponens 5 and 6. So what we had here was hypothetical syllogism, disjunctive syllogism, and modus ponens. Okay. Now let's look at the alternative solution. And you'll see what I mean, that like they're very similar, just a variation on it. But line 5, we could have started with disjunctive syllogism, right? So that would be the same thing. Line 3 and 4 disjunctive syllogism, that gives us not B. 3 disjunctive syllogism, 3 and 4. So we're saying which lines it comes from. Line 6, not B if, we're not using this anymore. Not B, plug in here, that gives us not C. So we can write not C from 5 and 1 modus ponens. By the way, you might notice that, you might wonder, I think this is the first time this has happened, where we went out of order. When premises are listed, there's no special significance in the order that they're listed. I mean, each premise is true on its own. It's essentially the same principle as in arithmetic when we say 5 plus 2 versus 2 plus 5. In arithmetic, for addition, that order doesn't matter. Sometimes we are taught to put the higher number on top and the lower number on the bottom. But even if we didn't, although the method we use of figuring this out might change, it might not be as efficient. The answer is, that's bad math. The answer is still the same, 17, right? In premises, I think I mentioned this in another video, but in premises, the sort of hidden operator is always and. 1 is true, and 2 is true, and 3 is true, and 4 is true. And it doesn't matter what order these are in logically. So we might sometimes find that the order that we use them is not the order of the form, as is the case here, where here we're using modus ponens, but our, actually, this would be modus ponens 1 and 5. But we're jumping around here, so maybe this wasn't a case of this. But when we have line 7, the point that I'm trying to make here is we don't have to necessarily go in order. So it could have been the case that we went backwards, that the first line of this is line 5, and the second line is some earlier line, and that we end up having 5, 1. But in this case, this is fine. Okay, now we have not C. And now we can say 2, 6 gives us D. So modus ponens again, 2 and 6. So in other words, this was a good proof. This was a good proof. But before we saw hypothetical syllogism, disjunctive syllogism, modus ponens. Down here we see disjunctive syllogism and then 2 different modus ponens. Okay, different paths, same destination. That's totally fine. All right. So this is the basics to proofs. I'm going to stop this video now. It's been about 45 minutes. I hope this is helpful. Check out, I would say if you need more help with this, reread chapter 11, and then also dip your toes into chapter 18. But I would recommend not going to chapter 18 until you've also seen the truth functional language well-formed formula video, which will help you out in understanding the symbols and the usage of it in chapter 18. Okay. See you next time.